Section 20.3, Voltaic Cells. A voltaic cell is also called a galvanic cell, and it's essentially a battery. And voltaic comes from the word volt, which is a push of electrons. So what's going to happen if you have a certain oxidation reduction reaction that's spontaneous, so it happens automatically. As soon as you put two things together, it'll automatically happen. You can actually ship some electrons through a wire, and those electrons, as it's being propelled through the wire, can do work on something that the wire is connected to, like a light bulb or something like that. So a galvanic cell essentially is a redox reaction that we are going to use to make what you know commonly as a battery. Okay, so in the jar here in the picture, I've got some copper ions. Okay, so this is not copper metal, it's copper 2 ions. Copper, remember, is the color of a penny, but copper 2 ions in solution is a really dark, beautiful blue. Okay, if you were to put some zinc, a piece of zinc in that, okay, put some zinc in that, some interesting things happen. Any of the copper 2 ions that are in solution, if they come close to that zinc and actually touch the zinc, electrons will automatically or spontaneously jump out of the zinc metal and into the copper. Immediately, it's no longer an ion. As soon as those electrons come in, it's no longer positive 2. Those 2 electrons have made it 0, and it is now not a copper ion, it's copper metal. And that metal is deposited onto the zinc. So you end up with a zinc, a atom of zinc that was solid zinc to start with, that loses electrons, and now it is no longer a solid zinc atom. It becomes a zinc ion. Okay, so let's look at it here. Here's a zinc atom. We'll do it right here. Here's a zinc atom. It loses some electrons, 2 of them, to the copper 2 ion. Copper 2, remember, is positive 2. So in order for it to become neutral again, it needs 2 electrons to cancel out that positive double positive charge. When that happens, it is no longer an ion. It is now a copper metal atom. And it sticks to the zinc, and the zinc ion comes out and immediately becomes zinc cation. It goes into solution. It dissolves into the solution. So what's going to happen eventually is that this piece of zinc is going to be eaten away, and it is also going to be coated with the copper. At the same time, the color of that distinctive copper solution fades into kind of a gray, which is the color of the zinc solution. So you're going to see a color change. You're going to definitely see that the zinc gets eaten up. It looks corroded, and it's going to be covered in a black sludge of copper cells or copper atoms. So it's not just happening with the electrons, you're also going to have some energy. So there's some energy that's going to transfer, and this energy is enough to send some electrons through a wire as long as you finagle it just right. Okay, now this is a voltaic cell. Essentially, it's a battery. It's a very kind of a complicated looking one, not what you're used to, but essentially it works like a battery. What happens is you've separated the metals and their solutions from each other, but you've also connected them in such a way that some charge can be equalized throughout the solutions. When you connect those 2 metals together, an electron, which normally goes right out into the solution, will instead go through the wire to go to the other side. So I'll try to break it down a little bit and give you kind of an idea of what's going on. Okay, so in the previous picture, we had some zinc. This is a zinc electrode here, okay, a piece of zinc, and it's in a solution of zinc nitrate. Okay, the nitrate, it really doesn't matter, it's just a negative anion, but the zinc solution, the zinc solid is in its own zinc solution. Okay, so because of that, the zinc and the zinc is not going to do anything to each other. The zinc solution and the zinc metal won't steal electrons or donate electrons or anything. If you were to put a piece of zinc metal in some zinc nitrate, nothing at all would happen. Nothing. Okay? On the other side, you're going to have some copper, a piece of copper, and it is in also a copper solution. So you have a copper nitrate solution. Well, nothing there is going to happen. So if you were to put copper in copper, nothing would happen. It wouldn't be like what we saw a minute ago when you put the zinc in the copper. If you put the zinc in the copper, immediately electrons are going to transfer. Okay, so you want to keep these electrons away from each other so that you force them to go through a wire. That's the idea of a battery. You want it to go through the wire so that those electrons can push something like a light bulb as it's traveling. Okay, now as soon as you connect the two metals with a piece of wire, still nothing would happen. All right, if you were to put zinc in some zinc nitrate, copper into some copper nitrate, and connect it with a wire, nothing at all would happen. No electrons would transfer. If you add a bridge, now in the previous example it was kind of connected in the glassware. Here you've got some gel, and all it is, it's just some sodium nitrate. It's just some charge. It's salt. It's a salt water. You could easily do this with a piece of paper towel that you put some salt water on the paper towel and just drape it over the cups. As soon as there's a path for the electrons to go back and forth, suddenly now it's going to start forcing. Okay, so what's going to happen is you are going to have electrons that want to go from the zinc to the copper. All right, so let's look at what's happening. First of all, reduction, remember, is when you're going from a ion to a metal. Okay, so reduction is going to occur at the cathode. You see that this is positive. I see cathode with a positive. H there is the plus, the cathode. You could say that reduction starts with a R and cathode starts with a C, and both are consonants. That's a good way to remember it. The cathode, or the positive terminal, is where you're going to get deposits of the copper. The copper is going to come out of solution and start sticking to the copper, piece of copper. So you're actually, the copper piece is going to add mass. Also, the copper solution is going to start changing color because that deep blue of the copper ions are going to start being depleted. And so it's going to kind of get wimpy looking. At the same time, the electron had to come from somewhere, and it came from the metal. And so the zinc that had the electron in it originally is going to lose those electrons, and the zinc atom is going to become zinc ion. And so the solution is going to get more and more concentrated in zinc cation. And the piece of zinc is going to start being eaten away. Okay, so this is called the anode. The anode always has to be replaced in a battery because the anode is being eaten away as the electrons are being stolen out of the metal, and that metal is being turned into a solution. So it's always going to be eaten. The cathode, or the positive terminal, is where you're always going to have something added to it. So in this case, copper added to the copper metal, and so it's going to gain weight, and the anode, which is the negative, is always going to lose weight. So at the anode, you're going to have oxidation. So oxidation and anode both begin with a vowel, if you want to think of it that way. And so this is going to be reduction. Reduction happens at the cathode, and oxidation happens at the anode. So the purpose of the salt bridge is then to make sure that the charges are balanced. Because if you were to start dumping positive charges, positive zinc cations in the zinc solution, or you would start taking away positive charges from the copper solution, what will happen eventually is that you wouldn't have any voltage, you wouldn't have any push on the electrons, and the electrons would stop working. So if you were to put a piece of zinc metal into some zinc nitrate, copper metal into copper nitrate and connect them with a battery or connect them with a wire, nothing at all would happen. Okay? But if you were to have some way for the charges to be made to keep balanced, okay, even a piece of paper towel that you put some salt water on is enough to keep a charge going. And if you were to use a voltmeter here to measure what the voltage is, you'll see that the difference between one half reaction, one chamber, and the other has a voltage. And that voltage is a push, and it's a push is enough to push the electrons through the wire. So once you have a salt bridge installed, the cations will move towards the cathode. So you've got the zinc cations will start migrating towards this, and will end up in this jar, keeping it positive. And then the negatives, as this keeps getting more negative, the negative will keep balancing here, and you'll keep the electric signal going. Here's what I mentioned before. Once you have a salt bridge and connected wire, some kind of a path that the electrons can happen, then what will happen is that the electrons will be sucked into the zinc. Okay, they'll be stolen from the zinc metal. Okay, and you'll end up with an atom that's turned into a cation. Okay, so you have a zinc, this is zinc 2 cation. At the same time, you're going to have the electron that has come all the way across. The electron is now on the copper. The electron goes into the copper sulfate, or I'm sorry, the copper ion. It becomes copper metal and then sticks to the copper. So the copper is going to gain weight and at the cathode, and the zinc is going to lose weight at the anode.